role at this point. The term is going now, and so it's going to be, attendance is going to be a little bit more flexible. Third point. Project papers. I need you guys to start doing some self-organization and get a sense of what you want to do. If for no other reason, then two groups will not be allowed to do the same paper. So the sooner you can get your request in, the sooner you can sort of lock in, confirm that paper. And it also gives you, more perspective for, if you will, negotiating. If somebody else really, really wants a paper, then, it gives a basis for discussion early rather than later. Okay? So definitely get on that. I had another paper that was sitting on my desk. I thought it was kind of interesting. It was maybe more poignant last year, because last year was the, 50th, 40th, 50th anniversary of the Kennedy assassination. There was a famous physicist, Luis Alvarez, who did a scientific analysis of the Broder film. And what's that? Zabroder. So whatever. See, I just tells you how much I really care about it. But it's kind of an interesting thing, because he had to do all kinds of really sort of new analysis to deal with the type of evidence that was available. And it is, the different things that he did are worthy of a paper discussion, because there haven't been very many examples of that type of a work that were published in any form of scientific journal. I'm sure there's all kinds of ballistic tests that are in specialized journals on investigation or whatever. But, so I'm going to post that one here too. That's kind of an interesting one. Everything has its pluses or minuses. Every single paper, whether it's experimental or whether it's theoretical, everything has an upside and a downside. And I'll tell you, if you're just skimming through the papers, the shorter papers oftentimes require a lot more background research, because there's an awful lot inferred and context leading up to those discoveries. For instance, Fermi's nuclear atomic pile measurements, a chain reaction. It seems it's a couple-page paper. It seems kind of short, but there's an awful lot of build-up to that. So don't assume, for instance, based on size of paper, that it really makes it more of a slam dunk than not. Definitely work on or focus on picking an idea that is interesting to you. And again, I'm always open for discussion. If you think there's something else, we can try to find it. If it sounds like something that there might be a fundamental paper related to. But again, more often than not, like the real interesting sort of new topics tend to be so far out there mathematically that the only way one at this level could really ever expect to address it would be to use Wikipedia and Joe Schmo, physics expert, discussing what it means, because those things you just cannot get your brain around in terms of the way that it is actually understood at that level. So, that's why the papers are sort of where they are, and the other issue is basically, what is it that the 20th century gave us? You could say the 17th century gave us physics, maybe the 18th century gave us, or I should say 18th century gave us physics, 19th century gave us thermodynamics and electricity, magnetism. 20th century gave us the atom, from which you could work backwards to electricity, magnetism, thermodynamics, everything else. So it really is kind of serendipitous that all of the papers that are easy to access in terms of relative size, etc., tend to be papers related to the discovery and understanding the structure and nature of the atom, which is kind of cool on so many different levels. Okay, so please please, please, please get on that, because I want to start making a tally. I'm going to try to send around a survey basically to use to sort of select your paper. I got to figure out a way to do it to make it mutually exclusive. So once one paper is selected, now you have to go to a secondary paper. Or alternatively, top 3 picks, and then I'll have to go through and look at timestamps of the papers. So I'll figure out the best way to do that, but the sooner you get a sense of what you want to do, the better.
You could do a Google Doc or something like that, just highlight it out.
Yeah, I could just put a survey on there and just have you guys type in your stuff. So I don't know, I got a few different ideas for how I do that, and it's ultimately in the worst case, there's a piece of paper, I mean, there's a million ways. I'm not too worried about that. I'm more worried about you guys and gals getting started. And also, it allows some encouragement maybe to start getting together even as it relates to study groups for this stuff. Because just like anything else, just like your engineering stuff, the critical mass is oftentimes really, really helpful with putting this stuff together. It really is. You sometimes just don't know what you don't know because you just never really thought about. And it's an opportunity loss. I mean, it's a grade, it's a required class and all that, but it's truly an opportunity loss because you're not going to get many more basic classes like this that focus on what's going on, not just how you calculate a mathematical model to get an answer. And I know for me that's sort of much more mushy educator speak, but it's the truth. And so take advantage of it. So otherwise it's just a wasted class. Hopefully you get your grade, but so much will ultimately add perspective down the road. Okay, so any questions on anything? I think I've covered the homework, project. I'll put that Zapruder film? Zapruder? Or film. The analysis of the Kennedy assassination. It's kind of interesting. So, kind of leave it at that. Now, where we're going is quantifying and really sort of establishing perspective on how we analyze electrostatic systems, or charge-driven, charge-constituent physical systems. And there's 2 different levels where it's interesting. At one level, it's kind of purely a matter of just getting a sense around how you model things and how ultimately it can be used down the road in any sort of practice. But on sort of a basic level, there's an underlying idea that is not particularly obvious at this point. When we talk about this idea of an electric field, we'll get into the specifics of it. But when we talk about this idea of an electric field, here's sort of what we know. You got 2 charges that interact, call it Q1 and Q2. I don't care if they're positive or negative. And you say, okay, well, what's going on here? Well, there's an electric force. Now, from a physics perspective, we're almost always concerned with what is the electric force, because we're almost always concerned with forces, because forces translate to disturbances, or how something is interacting with other things around it, and ultimately then how the consequences that are associated with motion, engineering, structural stability, thermal consequences, etc. However, there's a little subtlety to this, which is not obvious, may not be obvious for us in a deep sense, even by the end of the quarter. And that is that underlying these charge effects is a little bit more, I don't want to say more fundamental, maybe more fundamental mechanism or phenomenon, and that's the phenomenon of light itself. And even though we won't get a deep opportunity to spend on specifically the interaction between electric fields and the generation of magnetic fields and how that relates to light from motion of charges, our transformation of paradigm from just purely looking at forces to looking at a new idea, which is the idea of vector fields, is sort of that segue in a philosophical or in an intellectual sense to further exploring the idea of the mechanism of light itself without the need for dealing with forces per se and electric charges explicitly. So understand that in some ways the next chapter or 2 will tend to feel like, okay, well, it's really, in a way, it's just solving for f and this stuff. But on a deeper level, there's an underlying framework that's being built that if you take a modern physics class, or if we were to able to continue for, say, another month of the class, we could amalgamate it a little bit together and get away from any mechanical related idea and focus purely on the energetics of light propagation. We've done geometric optics, but at a more deep fundamental level, light itself. Can't, we won't, but that's kind of built into this. So at any point when it starts to feel like, if it does, if you think about it hard enough and you feel like, okay, well, it's not a whole lot different here, it's because it really isn't, but it's sort of setting the table for another level where we get to it. Now, for us then, the idea is basically this. We say two charges interact, and because they interact, there's this electrical force that's established between them. Without one charge affecting another charge, if this charge doesn't, if this charge doesn't exist, then there's nothing on in an electrical charge interaction sense that's happening to the other charge, and therefore it's sort of a non-issue. If you don't have an electric charge, you can't tell an electric effect on another electric charge. Right? You need one charge to detect another one. That's a fundamental rule of our technology. We have to use electrons, and we have to use electric charge to detect just about everything else we look at. Whether it's a gravitational interaction, whether it's atomic, whatever, it always comes down to this little electric signal. And that electric signal requires the disturbance of some electron in some little probe somewhere. It always comes down to that. So we sort of got that built in. However, this charge affects this charge. We get some sort of a thing going on here. Now, the second charge doesn't exist at all, but this charge is still here. One way that we can think of what this charge and the consequence of this charge being here is that it affects the space around it. Now, how do we know, or how might we infer that it affects the space around it? Put an electric charge here, and it does something. Well, I know because of the fact that I put that charge there, due to the other one being there, the space here, right? This charge is all the way over here, but the space here is somehow affected because when I put another charge here, something happens to it. And it's different than if I put the charge here, or if I put the charge out here. So just the mere presence of this charge has an influence, an electrical, a charge-based influence, if you will, on the space around it, plain and simple. And we refer to that influence as the electric field, or the vector field associated with the charge. So here's sort of how we approach the analysis in a simple sense, and and then the problems sort of go from there. So I'll make it some negative here. Make life a little bit easier. Okay, so we got two charges, and the idea is, okay, I want to know what the effect is on this charge over here. So let's assume that the only interaction, the only charge affecting this rightward charge is Q1. So we can define a separation or spatial vector that originates at the first charge, because that's the source of the disturbance, and is directed along the line of action toward the second charge. Well, then we would say that, well, what's the force exerted on this charge? Well, the electric force would be equal to, now up to this point we've been using this Coulomb constant. The textbook doesn't use it. We're going to quickly get away from it. For now I'm still going to use this K, the Coulomb constant, times Q1, that's the disturber, times Q2, that would be the disturbee, divided by the square of the distance of separation. And the direction I'm just gonna leave it generic and just say that the direction is in the direction of R. Now, because Q1 and Q2 have opposite charges, the product of the two will be a negative quantity. So, what does that say about the interaction between the two? It's going to be pointing opposite positive direction, if you will, or inward toward charge 1. In this particular case, since maybe I'll even just write it this way. If we looked at the magnitudes of Q1 and Q2, just for a perspective issue, we'd say it would be minus the product of the magnitudes in the direction of R. Now, I want to say it this way specifically. If instead, I'll just draw a second example. If this is sort of scenario 1, or A, let's look at a slightly different scenario with, for the most part, everything being let's look at a second charge that's positive instead of negative, that's separated by the same distance. All of the things being equal except the charge is now positive instead of negative. So the only difference between that and that is, I guess I better call this Q3. I just better give it a different name so we recognize that. And I'm going to add here that let's just assume that Q3 has a magnitude equal to Q2, but its direction is opposite. Okay, so if Q2 is negative, then Q3 would be positive. It's just opposite. Same value. So the electric force, we express exactly the same way, Q1, Q3, still taking the product of the charges. The sign matters when we express it this way, divided by R squared in the direction of R. Or we could write this as K, Q1, Q2, divided by, or Q3, excuse me, divided by R squared times in the direction of R. Now, to this end, we can say a couple things just by looking at this by analogy. If I start with the bottom one, maybe we just point out that with the exception of Q3, all of this stuff has to do with what was already there, both the point in space and the charge that's just sitting there affecting the charge that I'm looking at. If I look at this one, I could even look at it over here, suppose. Again, I've got the space, and I've got Q1. It's the minus in the Q2, or if you will, it's this guy here that affects ultimately what's going on with the electric force. Everything else is already set. Set the table there. Again, over here. So it's this guy that is the determining factor as far as what happens when you put the charge there. Everything else is just already there. Because of that, we say that the charge interaction in space, this electric field, is based on the magnitude of this charge and ultimately how spatially this charge affects the region around it, which is certainly related to how far away you are from that charge. And to this end, we might just note, I'm writing backwards here, so I want to say this. We might just note that if we separate but the affected charge. Okay, so Q2 or Q3. Then we're left with some physical quantity. And by the way, one way we could separate it and remove it would be to divide by that charge. So for scenario A, let's take the electric force, which was originally K Q1 Q2 over R squared, and let's divide this by Q2. In other words, I want to get Q2 out of it. Which requires I'm going to have to also do anything you do to one side, you got to do the other. I'm going to put it here, and that will allow us to eliminate that second charge Q2 from our calculation. And what we're left with then is K Q1 over R squared pointing in the other direction. Okay, just leave it at that for now. If I look at B and approach it the same way, whether or not it's positive or whether or not it's negative, I take FE for the second example, K Q1 Q3, and divide it, divided by R squared, there's Coulomb force. And divide all of that by Q3 now. I'm left with, not surprisingly, the exact same expression as Q1. Or I'm sorry, of the first example, example A. That makes sense. I mean, you remove the charge you're looking at, which may be different between the two. Everything else is the same anyway. This is the effect of this charge at any point around it. So we separate this particular quantity, this idea, and we say this is the electric field, or if you will, the vector field, vector influence of this charge Q1 on the space around it. What will determine the interactions, the observed forces, will just depend on what I put there. If I don't put it there, this calculation is still valid. I may not be able to sense it, it may not mean anything in a physical sense, but we assume that it's still there. So if I call this here the electric field associated with Q1, so this is just due to Q1, so I'm going to indicate that. Everything that has to do with only that charge and the space around it is another way of saying, if I put any electric charge at some location R, then this quantity E represents the electric force vector per unit charge at that particular location. The actual force just depends on how much charge and what direction and what magnitude, or I'm sorry, what sign it is. So this is, in fact, the electric, but it's the force per charge or per unit charge. Force vector at any position R.
You need like Q3 under that.
Oh, what did I do here?
Under the-
Oh, I'm
under
sorry,
FE
thank you, thank you.
here.
You know, I just talked in there, forget that, sorry. And you can see that it's the same regardless of the charge, just in our direct evaluation of the electric force on any charge over there. So this now becomes ever so, not so subtly, our new goal. Instead of focusing on the Newtonian aspect of Newton's law, trying to figure out what the force m times a is for everything, we make this little shift or adjustment and say, well, charges produce or have this associated electric field, which is a vector. Well, let's calculate or figure out how to calculate this electric field vector. Once we know it, then all we have to do is stick a charge there and figure out what that means in physical force. But even if we don't have a specific force or a specific charge there, we still got this basic environment due to the charges that are there. So that's the idea. So we go now from using basically Newton's laws and calculating force to now just looking for the electric field. Because once we know the electric field, now we can say this. If you want to solve or find the electric force on any charge, call it Q naught. Near Q1. All I have to do is figure out what the electric field is due to that charge. And if I had more than one charge, then I just have to include that and multiply it by this, by whatever charge I put there. And the positive or negative will determine the direction. So that's the paradigm. Now, and we need to spend some time, because the calculations and everything really funny. But if you notice, as we express it this way, we literally set up a mathematical mechanism that looks very, very similar to what Newton's second law looks like in the first place. Right? M times A, where A is really the gravitational acceleration. We sort of said it was motion in general, but we could also just say that the gravitational force, just for basis of comparison, that if we wanted to look at a planet, gravitational force exerted on something, we would say would be equal to that mass, whatever it is that's being affected, times G, which now maybe I just write as a gravitational field vector. Maybe we call it G. Now this tells me everything I need to know about how gravity affects. Now, the problem is before we just started with gravity, just said, well, it's mg, and now we throw normal force and all these other things. If we're just looking at a fundamental level, the gravitational interaction between two masses would be related to whatever this is, right? The Earth, for instance, instead of Q1, times the mass that's affected by it. So we very coincidentally created an electrical force model that exactly parallels our gravitational force model. And not only that, it turns out that by happenstance, electric forces look very, and the interactions, the charge-charge interactions, look very, very similar to mass-mass interactions with gravity. So we're kind of fortunate there. And that's sort of the high level, is that basically this is a gravitational model for electrical charges. Nothing more, nothing less. But for us, this is the problem. We always kept G fine, and we never worried about G. It was more, what is mg when we put a bunch of other crud there? The fundamental problem from this point further then becomes figuring out what the heck this E is. How do we calculate it? And then what does it mean as we move forward in terms of energetics and even charge production? This is the paradigm. So let's do some calculations to sort of put it in perspective. It's sort of a simple case now, but let's look at additional scenarios. So any questions on how this stuff fits together? I want it to be as common sense and sort of organic in terms of how you look at it as absolutely possible, because it should be. And for that matter, as people have pursued this field of study, there has been, along the way, a not so subtle discussion about the reality of fields in general. So, whether or not you accept the electric field as what it is, you use it as fundamentally, at least, a mechanism for describing how things that are not next to each other can somehow miraculously affect each other. So There's all kinds of hand waving built into that. How do you explain this here and this here, pulling and pushing on each other, whether it's gravity or otherwise? You've got to have some. Or we say it's the electric field. There's an electric field due to this charge just pulling out here. It's not really the charges because they're not anywhere near each other. It's the field that does it. Okay, so based on this, then there's a few sort of obvious things. First of all, and it's worth noting, if you have a charge, I'm just going to call it Q now. The electric field associated with this charge, because it's related to that Coulomb effect, will always be pointed, no matter where you are in space. If I'm out here, if I'm over here, it will always be pointed directly from the source outward. Now, what direction does that really mean? It means if I were to put a positive charge here, it would be repulsive. And the electric force on it would be pointing away. If I were to put an electric charge over here, with a positive, with the same sign as this, it would be pointing, the force exerted on it would be pointing, again, away. So, as we look at it, in our mind's eye, we can sort of say that for any given charge, the electric field is essentially this vector arrangement of arrows, the direction of which is the direction that a positive charge would be pushed or pulled. And it doesn't matter what direction, it's always going to be repulsive. The true numerical sign just depends on how you define your coordinate system. And conceptually, the closer the field lines are together, that's sort of an implication or an implied increase in electric field. So when you have the lines packed together, you've got a stronger electric field. When you're further away, where the field lines are much more spaced out, then it's a weaker electric field. And how does it extend? It extends as the inverse of the distance of separation. So if I'm here and I have an electric field vector value pointing away, if I go twice the distance, it's going to be 1/4 of its value. And you can see that for the way the field lines spread out. And the inverse, if I had a negative charge instead, call it Q prime, then the electric field would still radially look similar, pointing along the line of action. If I put an electric charge here, if I put a positive charge here, it's going to be attracted inward. So we say that the electric field, I should probably put it in. But the electric field, because of the force that would be produced, if I put a positive, attractive charge, it would be pointed in towards it. So, as a mathematical model, kind of like a free body diagram, an electric field for a positive or for a negative charge, if it's a point charge or a localized